So now that we are appropriately armed with the ability to do the chain rule, the ability to use the chain rule to come up with implicit derivatives, and we also know how to do trig derivatives at this point, I figured it'd be a good time to jump into the world of inverse trig functions and their derivatives. And just as a quick reminder before we get started, that there is notation for the inverse trig functions. And one is the notation on the left with the little -1 symbol, or as some of you may have seen, arcsin of x. And the reason why people use arcsin of x instead of this inverse sign notation is that this -1 is a bit misleading. It does not mean 1 over sine of x. This is one of the most common mistakes I see people make with this, because 1 over sine of x is the same thing as cosecant of x. But we're not talking about, the reciprocal function. We are talking about the inverse function, which are two very different things. So if you need a review as to what an inverse trig function is and why we use them or why we might care about them, I would encourage you to just quickly pause the video and head over to my Pre-Calculus 2 playlist and just glance through the video that's labeled inverse trig functions, because I think I do a really good job of kind of just introducing them and saying this is when you use them and these are the restrictions, etc., etc. But this video is more catered to people who know what they are, and we're ready to try doing some derivatives. So for this, it's kind of best to just start with the example, and I'll use the inverse sine of x to kind of get us started. So, let's say given that y is equal to the inverse sine, and I'll use both notations kind of intermittently, but I'll start off with the -1 notation first. So our goal is to solve for dy dx. Okay. Now the thing right at the beginning is the thing that makes this hard is not the fact that there's a y here. I know how to take the derivative of y. I know how to take the derivative of x, and heck, I even know how to take the derivative of sine. But I don't know how to take the derivative of sine inverse, right? This is not an exponent, so it is not as simple as just bring down the -1 and write sine to the -2. This is not what you do, because that is not a -1 exponent. It is a notation to indicate to the reader that we're talking about the inverse trig function, the arcsin of x. So the thing that makes this challenging, right, is that we're dealing with the inverse sign. So one strategy that we are going to learn and we're going to get better at, kind of as the class goes along, is if you're ever given something that doesn't look like you know how to take the derivative of it, a good strategy is, can we rewrite this, right? Can we rewrite this in a way that we can take the derivative of it, right? That we can take the derivative of it, okay? And the answer is, of course, yes, in this particular case. So I like inverse trig derivatives because it's the first time that we really start to use some different thinking than what we traditionally do for doing derivatives. It's not just rote memorization. We have to kind of think critically. And so what we're going to do is we're going to kind of come on over here, and we're going to remember that y equals sine inverse of x. If I were to take if I were to take sine of both sides, right? If I were to apply the function sine, so I have sine of y, and then I have sine of sine inverse of x. So I've applied sine to both sides, right? Just like you can raise both sides to a power of e, or you can take the square root of both sides, right? I can do sine of y is equal to sine of sine inverse. You're going to notice that this sine and sine inverse here will cancel, and we're just going to be left with sine of y is equal to x. So it is worth remembering that y equals arcsin of x is the same thing as sine of y is equal to x. Now, why am I making such a big deal out of this? Well, because this is now something that I know how to take the derivative of every single part of it. And so now that there's nothing here that I don't know how to take the derivative of, I'm now going to apply the derivative operator to both sides, and we're going to do the derivative of sine of y is equal to the derivative of x, right? Because our goal is to solve for dy dx. I need a dy dx to pop out, so I need to take the derivative, that way it shows up. Well, let's start with the right side. That's the easier side. On the right side, we're just going to be left with the derivative of x, which is just 1. And on the left side, we are going to use the chain rule as always. We have an outside function, we have an inside function. So the derivative of the outside is going to be cosine of y, and then times the derivative of the inside, and the derivative of y with respect to x is dy dx, or y prime. And so this is super useful for us because this tells us dy dx is equal to 1 over cosine of y, right? There you go. That's the derivative, okay? Now, I am going to pause here and say that we are going to keep going a little bit. And what I mean is that, yes, this is technically an implicit derivative, right? This is an implicit derivative, but I claim that we can, I can use this to get an explicit derivative, right? I want to get it. So step 2, or part 2 maybe, but I'll just write step 2 is, can we get an explicit derivative? Because explicit derivatives are really nice. We know how to identify them, right? They only contain x's in them. We can do things like talk about the domain. We can figure out when the derivative equals 0, a whole bunch of really easy stuff. And so we are going to try that. Now, at first glance, you might say, well, I don't know how we're going to do that because I have cosine of y here. And in order for this to be, you know, an explicit derivative, I can't have any y's. So the question now is, how do we get rid of this y, right? Is there a relationship that we have between y and x? And it turns out that, yeah, remember that at the very beginning, we had y is equal to the inverse sine of x. And moreover, we could have that sine of y is equal to x. So I just want to point out, at this point, students tend to do this thing. So they tend to say that dy dx is equal to 1 over cosine of, and they say, well, y is equal to sine inverse, so I'm just going to have of sine inverse of x, like so. And technically speaking, this is correct, right? Technically speaking, this is an explicit derivative. But for the sake of homework, and for the sake of practice, and for the sake of more real-world use, I am going to have us do a slightly different approach in coming up with the derivative. And the reason why is because if I plug in like x is equal to 3 here, I don't think any of you can evaluate this in your head without using a calculator, right? You know, could you tell me what the domain of this derivative is? Could you tell me if there's any maxes, right? Could you tell me if there's going to be, you know, could you solve for when it equals 0, things like that, right? This thing's going to take a little bit of work. And so what I'm going to do is while this is technically speaking not incorrect, I'm going to erase it for a second, and I'm just going to put back that 1 over cosine of y, okay? And what I'm going to do, this is the part that's a little weird for students, is I'm going to use the fact that I have this relationship between x and y that doesn't have any inverse trig in it. So specifically, we're going to use the fact that x is equal to sine of y. And now let's take a moment and just think about what the heck this even means, right? If x equals sine of y, this means that there's some triangle, right? Like that there's some triangle with some angle. What angle? The angle is going to be y. So there's a triangle with some angle, and sine of that angle, which is sine is opposite over hypotenuse, is equal to x. Which means that one of these sides is x, right? The opposite side is going to be x, and the hypotenuse is 1, right? This means that we have this triangle, that this triangle exists where sine of y is equal to x. And so all we need to do is figure out what cosine of that same triangle is. It's super duper slick. It's a really, really cool math trick. And the idea here is that, well, cosine, right, cosine of y should be the adjacent side over the hypotenuse, right? That's cosine, SOHCAHTOA. I know the hypotenuse is 1. What's the adjacent side? Well, we can figure that out because, let's pretend that I don't know what this is. I know via the Pythagorean theorem that, my first side squared plus my x squared should be equal to 1 squared. And this thing is going to give me that, my unknown side squared is going to equal 1 minus x squared. And that's going to tell me that, this missing side is going to equal plus or minus the square root of 1 minus x squared. And I want to point out that, just simply because we're talking about the lengths of the side of a triangle, we're going to ignore the minus sign that pops out here when we take the square root, and we're just going to have the positive version of this. And so what this means is that this missing side right here is just the square root of 1 minus x squared, and that means that cosine of y is equal to the square root of 1 minus x squared. Technically over 1 because adjacent over hypotenuse, but that's it. That's what cosine of y is. And so if we zoom out just a second and think about what the heck it was we were doing, the goal, right, we got the derivative in about 2 seconds. We said, the derivative is 1 over cosine of y, but we just basically now figured out that in terms of x's, written as an explicit derivative, that this derivative is 1 over the square root of 1 minus x squared. And now when I ask you something like, what's the slope going to be when x is equal to 1/2 or something, you can do it, right? I can do this with a little bit of mental math, and I could, come up with 1 over the square root of 3/4 and call that my slope, right? But it would have been much harder if I had written the answer as 1 over cosine of sine inverse of x, right? I guess, but, this one's super nice, and it uses this really fun idea of building triangles, which is a skill that we're going to try to develop in this class, because we'll actually use it a little bit down the line as well. So I'm going to do one more example because I know this stuff is a little bit weird. So let's start completely fresh. Okay, so for example, so let's say given that y is equal to let's do cotangent, and let's spice it up a bit. Let's write 2x minus 3 on the inside. Okay, so we have one of the inverse trig functions, arc cotangent of 2x minus 3. Solve for dy dx. Actually, here, I keep writing dy dx. Let's say solve for y prime in terms of x. In terms of x without using inverse trig. So what I mean is I don't want any inverse trig in the final answer, okay? And so we're going to say, okay, well, the very first thing that I'm going to do is I'm going to recognize, okay, I can't really take the derivative of this as is, right? I don't really know what the derivative of arc cotangent is. But step 1, let's just rewrite this thing in a way that we can understand it. So I'm going to switch back to the inverse notation with the -1 sign, and I'm going to say, look, if I take this thing here, which is cotangent inverse of 2x minus 3, if I take cotangent of both sides, it should just leave me with this equation. And now, step 2 is I can take the derivative of both sides because I know how to take the derivative of everything here. So on the left side, the derivative of cotangent. Okay, so how I think of this is I think of the derivative of tangent is secant squared. So the derivative of cotangent should be cosecant squared, but with a negative in front of it because this is a co. So this is going to be negative cosecant squared of y. But don't forget, we have the chain rule times the derivative of what's on the inside, which means times dy dx. And now on the right side, when I do the derivative of the right side, I'm just going to be left with 2. Okay, great. And so this immediately gives us that dy dx is equal to negative 2 over cosecant squared of y. So we're on our way, and I'm going to put a circle around this because we're making really good progress. Okay. So at this point, the last thing that we need to do is really deal with the fact that I have things in terms of y here. I have an implicitly defined derivative. We would like it to be explicit in terms of x. So we are going to use this earlier knowledge. We're going to use that cotangent of y is equal to 2x minus 3 to get cosecant of y. Because once I know what cosecant is, then I know what cosecant squared is, and we'll be done. So the first thing that we'll need to remember then is, cotangent. All right, what sides? So this means that there's a triangle, right? There's some triangle that exists, some right triangle, ta-da, with an angle. That angle is going to be y. How do I know that? Because it says cotangent of y, right? The input to a trig function is an angle. Cotangent of y equals 2x minus 3. Okay, so cotangent. Well, tangent, soca, toa, is opposite over adjacent. So we're talking about adjacent over opposite. And in this case, it equals 2x minus 3, which means if I let my adjacent side be equal to 2x minus 3, and I let my opposite side be equal to 1, now I have built this triangle that has the relationship that cotangent of y is equal to 2x minus 3. And so now we're cooking. Because in order to get cosecant, right, cosecant is 1 over sine of y. And yes, you do need to know your trig functions. You need to know their relationships. And so in order to know sine, I need to know opposite, right? Sine is soca, toa, opposite over hypotenuse. So we need to figure out what the hypotenuse is. No problem. We're going to use the Pythagorean theorem once again. We're going to say that, okay, 2x minus 3 squared plus 1 squared should equal the hypotenuse squared. And I could multiply this out and collect like terms. For now, I'm just going to leave it. I'm going to say that it's 2x minus 3 plus 1, squared, plus 1 is equal to the hypotenuse squared. And then in order to get the hypotenuse by itself, we're going to take the square root of both sides. A plus or minus shows up, but we're going to forget the minus one just because, we're talking about the sides of a triangle for now. So we're going to get the square root of 2x minus 3 squared plus 1 is equal to the hypotenuse. And so that means, right, now that I know what this entire side is, now that I know that, we're going to get that sine of y is going to equal 1 over all that square root stuff. So 2x minus 3 squared plus 1, which means that 1 over sine is just going to be the flippity-flip of this fraction. So 1 over sine is actually just going to equal the square root, aka cosecant, equals the square root of 2x minus 3 squared plus 1. And so now that we have that, we just need to remember that what were we looking for in this problem? We were looking for cosecant squared. And so we're going to take this thing that we just found and square it, and squaring is just going to get rid of that square root symbol. And so when the dust settles, we're going to finally get that dy dx is equal to negative 2 divided by cosecant squared, which is going to be 2x minus 3 squared plus 1. And you could leave your answer like this. I actually probably would end up multiplying all this out and collecting like terms, but if you leave it in this way, that'll be fine too. That's still full credit. Okay, so inverse trig functions are a little bit tricky. They require a tiny bit of legwork to get it in this explicit form with just x's, but the thing you're rewarded with is if I give you an x value to plug in here, it's very easy for you to algebraically tell me what the slope of this function would be, right? So, this particular one, we started with y was equal to the inverse cotangent of 2x minus 3. You could plot this into Desmos and see what this looks like. And, you know, this thing that we just figured out over here will tell you what the slope of this function is at any particular x value on this original graph. All right, so that's going to do it for inverse trig derivatives. We only have one more thing that we're going to learn about this week, which is logarithmic derivatives and exponential derivatives. So when you're ready to have your mind blown one more time, head on over to that video.